This is Dr. Muhammad, and this is another video under Dynamics of Structures, Multi-Degree of Freedom Systems. And today I'm going to talk in this video about the solution of the equation of motion for undamped system. So it is highly linked with the previous lecture because I have explained some principles, important principles in the previous video. So I hope that you can visit the previous video before and listen to it or watch it well, and then you can get engaged easily in this one. Okay, so let's start now with the solution of the of the equation of motion of for undamped system. So let's start first with putting the equation of motion that we usually use whenever that we are dealing with undamped system. So first of all, the equation of motion is going to have different terms, as we can see. In the left hand side we are going to have the inertia term, and then we're going to have another term which is related to the stiffness or elastic force term, and after that we are going to find in the right hand side we are having zero vector here. This zero vector means that we do not have any forced vibration. There is no forces here are being applied on the system. It is undamped. It is a system without any forcing functions. And in the same time we do not see the damping term that is usually we can find in the equation of motion, right? So no damping term here because we are talking about the undamped system, because we are working on the undamped system. Okay, so this is the equation of motion, the mass matrix times the vector of acceleration plus the stiffness matrix times the vector of displacement equals to 0, or the vector of zeros. Okay. So first of all, in order to solve this equation, let's clear here. In order to solve this equation, we need to assume some assumption. We need to assume that the Eigen problem has been solved. The Eigen problem has been solved. What is the meaning of Eigen problem here? This means, if we're going to here a little bit, the Eigen problem means that the mode shapes already we know. So we know like phi 1, phi 2, phi 3, which are the mode shapes that is going to come out from the Eigen problem solution. And of course the corresponding eigenvalues, which are the natural circular frequencies. Okay, the eigenvalues in our case or in this problem, it is going to be omega 1 squared, omega 2 squared, and so on. So this is going to be our natural circular frequency, omega 1, omega 2, omega 3, and so on. Okay, so this is the two main assumptions that already we need to keep in our mind. How to obtain these mode shapes and natural circular frequency? Please revisit like 3 or 4 videos before, and you are going to find that we have examples and we have explained it in detail regarding how to solve this eigenvalue problem. Okay, now let's go to the solution itself. What is the solution for our case? So the solution here is going to be, as you can see here, in the left hand side it is going to be the displacement vector, which is, we call it the response. Okay, you can say this is the response or the displacement vector due to this motion that is going to be there. And this displacement vector is consisting of u1, u2, u3 until un, which is the number of degrees of freedom that we have, how many degrees of freedom that we have in our system. Okay, so 1, 2, 3, 4, 5, and whatever. So it is the n degrees of freedom. And here we have the t variable because we are changing with time. We want to describe the motion of this system at different times. Okay, so this is the left hand side. The right hand side here is going to be a summation. The first thing that we can see, it is the summation. It is sum of things, sum of some terms. We're going to start from n equal to 1 and end with which is small n equal to 1, and end with capital N or uppercase N, which is, this is the degree of freedom. If we have 1, 2, 3, 4, 5, whatever, then it is going to be 5 degrees of freedom, and this n is going to be 5. This means that based on the degrees of freedom that we have, we are going to have different terms. So we're going to have n terms here. And there is a summation. This summation, it has significance, which is the sum of terms, not one mode shape. This means that if we have different mode shapes, every mode shape is going to contribute to the response of the system. So this is the significance of the summation here. It is additive. We are superimposing the contribution from different mode shapes. Okay, so this is the significance or the meaning or the interpretation of the summation sign here. After that, logically we are going to consider, we are expecting the mode shapes. Mode shape means that it is what is the pattern of motion that is going to be or being expected, okay, from the first mode, from the second mode, from the third mode, and so on. So this is the mode shape, and the definition of it already we have explained it before in the previous videos. So this is the significance of this term, which is the vector. And then it is multiplied by something. As you can see here, this is what we can see. First of all, we are going to see within the parentheses here, the square brackets here, we are going to find that we have an and bn. Means that an and bn, as I put it here, they are constants obtained from the initial condition. Okay, what is the meaning of this again? So the numbers here, or these constants here, they are having significance. The significance is the response of the structure is going to be affected by the initial condition. What is the meaning of initial condition? It is at t equals 0, what is the response? Okay, we do not know it. And at t equal to 0, what is, this is the displacement, what is the velocity of the system at every degree of freedom or at every coordinate, right? This is the meaning of the initial condition. Commonly we can get, or we can have this, it's known information for us, we can use it directly. So the contribution of the initial condition is important. Here we're going to find that an and bn, they are representing the initial conditions. Okay, they are representing the initial condition. Okay, and the last thing is cosine omega n and sine omega n t. It is sinusoidal functions. This means that our system, or the degrees of freedom, they are going to be affected, or they are going to show pattern that is composition of cosine and sine. Cosine and sine. And then, of course, with different, we are talking about different time, t, this means that changing with time. And omega n, which is inside here, it is the contribution of what? Exactly, the natural circular frequency of the system. The natural circular frequency of the system. So let us clear everything here. So now this is the solution of our system. From where we got this solution, it is very similar to what or from where that we have obtained it for the single degree freedom system. You can revisit the single degree freedom system in the early videos or early lectures. You are going to find from where. It's very simple. Okay, as I said many times, it's important for us to know the significance of the terms and the equation rather than to know how we have derived it. Derivation is very easy and it's found in the textbook, and you are going to understand it easily because it's mathematically sound, no problem with it. But what I found that most of the people, they are missing is the significance of the terms. Okay, so now summation, it has meaning for us, contribution from different mode shapes. The mode shape amplitudes are going to be contributed through the vector of mode shape amplitude. The initial conditions are going to be represented through an and bn, the constants. So initial conditions are going to affect the response through an and bn. Then the response itself is going to be sinusoidal because we have cosine and sine. And there is effect, or the last thing is the effect of the natural frequency of the mode shape itself. So every mode shape is going to contribute with its modal amplitude and the natural circular frequency. So this is the solution for our equation. This is the solution of our equation, general one. But again, the most difficult part, let me clear here, is everything is okay. It is omega here already. We already have obtained, or we know how to obtain it, as we said before, from the Eigen problem. And the modal amplitude vector, already we know about it. Then the summation, it's okay, it's something mathematical. What is going to be always obstacle for us is exactly the constants. Omega an and bn, they are the constants. This means that we need to dive into the initial conditions and try to find how we can represent them through an and bn. So this is our main problem from now on. This is our main problem from now on. Let's clear and move on. Okay. Now we need to find an and bn. As we said, they are our main unknowns now. Okay, if we could obtain them, then the solution of the equation of motion is going to be in our hands. Okay. From initial conditions, we need to know. From the initial conditions, we need to know the displacement and the velocity. The displacement and velocity. So we need to know the displacement vector and the velocity vector. The displacement vector and the velocity vector. Okay, and if you look here, we are going to find, of course, at t equal to 0, this is at the initial at the very first beginning of the motion. Okay, so regarding the displacement, we know the displacement already, because already it's in the equation itself. We know u of t equal to blah blah blah. That is already we know it. Okay, now we want to know what about the u dot, which is the velocity. What is the velocity, so that we can substitute in the equation? So we need to derive the equation. We need to derive the first equation. So u dot of t equal to the summation as it is from n equal to 1 to capital N, the modal amplitude as it is omega. N is going to be taken out because of the derivation. It was cosine here and sine, so it is going to be sine and cosine. Now let's have a look on the equation. So here in the equation we have cosine omega, and here sine omega n. So whenever that we derive it cosine, it is going to be minus sine, and the sine is going to be cosine. Okay, so this means here, let's go back. So this means that we have sine omega nt here, and the minus is here, and we put omega n here, and this is going to be cosine. It was sine before, and then omega is going to be outside also because of the derivation. So we have this equation now. We have this equation. Okay. Now at t equals 0, u of 0, which is the displacement. This is the displacement vector. This is the displacement vector. We are going to find that the summation is going to be from n equal to 1 to n, the modal amplitude vector times an, right? Because we have here an, first an is going to be multiplied by cosine omega nt, plus the other one, bn, is going to be multiplied by sine omega nt, right? This would be 0, because sine 0, it is going to be 0, and cosine, in this case, cosine omega n t, which is cosine, let me check this, please. I want to check. So here, yes, we have cosine here. So we have cosine omega nt here. Okay, so cosine 0. In this case, it is going to be 1, and sine 0, it is going to be 0. So bn would vanish, and we are going to left with an only. Okay, that's right. Let's go back here. So in this case, we are going to find that our modal amplitude vector multiplied by a constant called an. Okay, this is when it is only at the initial condition at u of 0, when t equal to 0. Okay, now let's move on to the next part. Now we want to get the meaning of now we have, yes, this is the displacement vector. Okay, and let's go to this displacement vector and check what are the things here. So if you look to this summation, it is going to give us something like this, which is phi 1, 1, phi 2, 1, phi until phi n1 times a1. Because a1, this an is going to be a1 for the first mode shape. And then it is going to be a2 for the second mode shape. And it's going to be a3 for the third one. And it is going to be an for the n mode shape, and so on. So we are going to have this summation. As you can see, it is a little bit cumbersome, a little bit long, right? And when you are going to put it in equations, so it is phi 1, 1 times a1 plus phi 1, 2, a2 plus phi 1, 3, a3 plus, and so on. And then we're going to repeat it with the second line here. It is going to give us these values, right? If you look, we're going to have, this is really long, right? We're going to find that we are having in algebraic linear equations in a1, a2, a3 until an, right? What do you think about this? Yes, as you're expecting, it is a bit difficult. How we are going to solve this? We have many degrees of freedom, many equations, and it is going to be really time consuming. Okay, so we need to find what? Yes, technique to make it easy for us. Okay, if there's something that we can develop or find to make it easy, and the problem is going to be doubled here, because simply for Bn, it is the same also. Look here for Bn, so I mean that for the velocity vector, when we are going to equate it with the summation of these modal shapes times omega n times Bn, if you are going to make it, will be the same as before, but instead of an, it is going to be Bn. So we are going to have also in algebraic linear equations in B1, B2, B3 until Bn. Okay, still it is difficult, a bit difficult for us, time consuming. Now we can think about something that we have done before, okay, and maybe it will make our life easier regarding the computational effort here. Okay, so I think that we need to look deeper into the equation and think about it. Solutions or solution of the in-algebraic linear equations for an and Bn is time consuming. Okay, time consuming without a doubt. So let us ask this question now, which is there another way for us to solve it? So now I think that we need to look deeper into the equations. Okay, look deeper to the equations. Again, we have these two equations. Look to the original equation again. U node, this is the displacement vector here. We have the velocity vector here, equals this summation of n equal to 1 to n, vector called modal amplitude times constant. And for u dot node, similar equation, but here it, instead of an, it is Bn times omega n, constant also. This is a constant. Okay, this is constant. Does it remind you with something? Exactly, what you are saying is right, which is in the previous lecture we have mentioned about modal expansion. Do you remember modal expansion? Yes, we remember it well, because in equation 8 in the previous lecture I mentioned before that we can decompose or represent any vector, which is u, any vector u, this is n by 1 for example, as a summation of different vectors qr times phi r times qr, which is, this is the modal coordinate. Do you remember it from the previous video? Please, it's very important to look to the previous video before watching this video, because it would give you a lot of information. So now it is pretty similar to what we have, right? We have everything here, so we are having everything here. It is here, it is as if we're talking about qr here. This is phi n, which is like the phi r, and the summation here, it is the same as the summation here. And this is u node. It is the displacement vector at the initial condition. It is known for us. Do you remember in the previous video when I was saying that you might ask me that, well, which one that we are seeking for QR or the displacement, and I said to you that you are going to realize this, the answer, or you are going to understand why we are bringing the relation between the two now. And I said to you that we are going to assume that we know the response, which is not common case actually. But here in the initial condition case, it is going to be important, because commonly we know, or actually we know the initial condition, we know the displacement vector, right? And we know the velocity vector as well. It is given for us. Okay, so now we can realize that QR, it is important for us, and it is going to be known if we know the main displacement, or the main vector in the left hand side. Okay, let's clear something here and go. So they look like the previous equation we studied in the last lecture regarding this. So they are very similar now. So we're going to consider them as we have done with the modal expansion and the modal coordinates. We're going to use this technique for the solution. They are going to save us time in terms of, as we said, it is going to save us the time for solving this these equations, this n algebraic equation. So using QR and the technique of modal coordinate, okay, or the modal expansion of displacement, is going to help us a lot in solving these equations. Okay. Okay. Now let's go down here, and I think that we can erase, and then let's go to the next next slide. So here, in this case, using equation 8, which is the equation that we know well, this is equation 8, the modal displacement, or the modal expansion of displacement. Okay, so we're going to use, will save us the effort for obtaining A and B. That's right. We can say that U node, okay, which is U of at the initial condition at t equal to 0, equal to the summation of n equal to 1 to n of phi n, which is the modal amplitude vector, times qn of node. We are going to call it like this: the modal coordinate that is related to the n mode. And between parentheses 0 means that it is for the initial condition, or talking about initial condition, because maybe later on we are going to have other cases not at t equal to 0. Okay, so q, it means modal coordinate, n means that for specific or particular mode, and between parentheses 0 means that it's for initial condition. This is actually, it is an. It is an. I'm not claiming anything except that this is considered to be an, the constant that we are seeking for. And for the displacement, it is going to be the same, but instead of multiplying by omega n times bn, it is going to be qn, because this is particularly for this n mode. Okay, and between parentheses it is 0 because it is for the initial condition, and here we're going to put dot, as if it is similar to the dot here, which is like it is initial condition for, we're talking about velocity. That's the meaning here. Here also we're talking about velocity, so we're putting this dot here to distinguish it between the other qn here. Okay, okay, so now let's move on. Now remember well that in this equations, an here, in this equation, so this qn, actually it is equal to an. From where? From this equation. Remember, this is our main equation that we were talking about. Okay, and this term, which is, I highlighted it in green, this is omega n bn, which I am going to put it here as qn dot node. Okay, so I hope that you understand the meaning now. And this is actually, I put them here where that qn, remember, this is modal coordinate for particular mode shape at the initial condition equal to an. This is related to the displacement, okay, vector. For velocity, which is the second term here, or this the other term here, it is going to be for particular mode shape, it is for velocity, and it is for initial condition. So three things. Okay, and this is modal coordinate equal to omega n bn. So it is another constant. Okay, it is constant. Well, do you think that it's going to save us the computational effort instead of using or solving in algebraic equations? Using this would help us? The answer is yes, it is going to help us a lot. It is going to help us a lot. Okay, so I think that we need to clean up here. Okay, and let's go to the next. Let's pause here. Okay, so now we are going to substitute by substituting in the equation that we have, which is our solution, the equation of motion. We're going to find that u1 of t and u2 of t until un of t is going to be in the left hand side, and the right hand side we have our an and bn. So we are going to put instead of this our modal coordinates. We are going to put them instead of that. So let's move on a little bit here. Yes. So we can say and claim that an and bn, they are the constants. Okay. Then this an is going to be exactly qn node, and this bn, it is going to be exactly q dot n node over omega n, right? Because this is what we have explained it before. The constant itself, qn node, it equals to omega n times b. Okay, omega n times b. Okay, now we have this. This is the final, this is the solution of the equation. Now we have qn node and q dot n node over omega n. Then we're going to put them between parentheses here, and then we're going to give them a nicer name here. Let's clean and let's go down a little bit to understand it. So here our displacement response is going to equal the summation of mode shapes times this two terms, the two terms here. Okay, and we are going to, for brevity, we are going to put them into one like one term here. We are going to call it qn of t. Qn of t. What is the meaning of this? It is qn, it is for particular mode, the modal coordinate at any time t. Remember, before we were talking about qn node, which is at the initial condition. Now we're talking about at any time. And this is going to be, the modal coordinate is going to be composed of two parts. One part, which is indicating or taking the effect of qn node, which is, what is qn node? Exactly, displacement vector. And at initial condition, we can say it initial, okay? Initial displacement vector. And here, q dot node or qn dot node over omega n times sine omega n t. So this takes into consideration what? Exactly, the initial velocity vector. This is the term. So omega nt, it is actually modal coordinate at any time, because we have cosine omega nt and sine omega nt. So we have the parameter t here, and it takes into consideration two parts: the contribution of the initial displacement vector and the contribution of the initial velocity vector. So they are in one term here, which is qnt. Let's clean everything to make it clearer for us. Okay, so now, and this is equation, we're going to call it equation 11. Okay, so now the response we are seeking, again, do not lose the guidance here. Our compass is that u of t, it is the response. This is the solution of the equation. We want to know what is the displacement at different times for each degree of freedom. And we are claiming that the right-hand side is going to represent the left-hand side. So the right-hand side is giving us and telling us that the contribution from the mode shapes is going to be through summation of all mode shapes multiplied by the modal coordinate associated with every mode shape. Okay? Remember, QNT equals to Qn node cosine omega nt plus Q dot n node over omega n sine omega nt. Okay? This is what we are going to call it equation 12. I'm going to recall these equations the next lecture. Okay, so again, what is the meaning of n here? It is for any particular mode, in any particular mode. T, why it is t here? Because it is changing with time. We're not describing a specific time here. It is generic, it is general. Okay, then this term, it signifies what? What is the significance of QNT? QNT means that the modal coordinate that is going to be used for scaling the mode shapes to take into consideration two parts. One part related to the displacement, initial displacement vector. The other part is related to exactly the initial velocity vector. Let's clean and read what I have put here. This is the one thing that we are having. So QNT, this is its role, multiplication of omega n. And then we're going to give it a kind of definition here. The first part, the first term, as I put it here, this term is the contribution of the initial, remember, initial displacement vector on the total response. This is the total response here. This is the total response, okay, which is through Qn node. Okay, through Qn node. And remember, this is through this channel, through Qn node, because the other one, cosine omega nt, it has nothing to do with the initial conditions. Okay, and sine omega nt, it has nothing to do with the initial condition. But Qn node and Qn node in over omega n, or this item in specific, okay, they are providing the initial conditions. This means what? Our total response is going to be affected by the initial displacement vector, and it is going to be also affected by the initial velocity vector from this Q dot node of n. So this term, the second term here in this equation, in equation 12, it means that this term is the contribution of the initial velocity vector on the total response through Q dot n node. It is the contribution of the initial velocity vector on the total response. Okay, this means that if I have Qn node equal to 0, what is the significance of this? The significance is the displacement, the initial displacement vector would not affect anything in our total response. And what if that I have Q dot n node equal to 0? This means that the initial velocity will not contribute to the total response. It has no contribution. So we can assume, or we can claim that the channel through which initial conditions are going to affect the total response is Qn node and Q dot n node. They are the channels. This is for displacement. This is going to be for velocity. Okay? This is going to be for velocity. Okay, so this is actually regarding this part. I hope that we have covered it well, and let me wrap up what I have said, because after that we're going to talk about an example that is going to help us in understanding. But I want to go back again and recap what I have mentioned from the beginning, so that you can understand what are the main steps involved here. Okay, so first of all, So first of all, we want the solution of equation of motion. As you can see here, this is our equation of motion, and we do not have any damping, no damping term. So we try to solve our equation of motion. So first of all, we were seeking for a way, okay, for the solution. After knowing the mode shapes and natural circular frequency, so we know some parts of the equation of motion, which is related to the natural circular frequency and the mode shapes. They are obtained from the eigenvalue problem solution. So it is okay for us. We know them now. When we are going to solve, we found that if we know the mode shapes and omegas, it is okay. But we found that we have some constants. These constants, an and bn, they are representing the initial conditions. So we need to find a way for the solution. When we tried to solve this, we found that there is some problems here, because we are going to have an algebraic equation of equations to solve our for our a and bn. So we found that we are going to have like an algebraic linear equation, and the similar would happen for bn. So we're going to have the same case here. We are going to have bn, and we are going to find that we are facing the same problem here. So this means that we are going to have an algebraic equation, linear equations for b1, b2, and b3. So it's not good for us. We need to find another way. When we seeked for this, we found that we have something. So the way that we have described before regarding the modal expansion gives us solution, actually gives us some hope, that we found that our equations, they are very similar. If we look, they are very similar to the modal coordinates, whether for the displacement or for the velocity. So in this case, we are going to use what we have learned before in order to solve our equation, and we are not going to go through the algebraic linear equation. They are going to be we're not going to solve them anymore. After that, we claimed that this equation, when we are going to use it for representing u node and u dot node, which means that the initial displacement vector and the initial velocity vector, we found that we can use this modal coordinate here, and we are going to give it specific designation, qn and qn dot. And when we are going to solve our equation, we found that, well, if this is the equation, this means that we are going to obtain qr from what we have explained in the previous lecture. Our main u here, it is going to be something known for us, whether it is going to be the initial displacement vector, as we said, or it is going to be the initial velocity vector. Let's clear this here. Okay, so initial velocity vector, okay, it is going to be here. So this means that we have now the ability to solve, because we know the initial velocity vector, we know the initial displacement vector, the mass matrix commonly given, the modal amplitudes vector already are calculated before. Then we can obtain qn node and q dot n node. These are equation 9 and 10, because we are going to use it in the next lecture. Okay, so let's clean, and then after that we obtained, or we going to solve for our equation, and we found that our equation can be solved easily with this qnt, and we said that qnt, it is going to be multiplied by the mode shape under the summation, and then this qnt is going to be represented by two different terms. One term is taking into consideration the initial displacement vector, the other one is initial velocity vector, as I have explained, and then based on that we are going to solve our equation. How we are going to solve it, we are going to see in the next example. I'm going to show to you how you are going to use the modal coordinate to solve your equations and how we are going to utilize what we have obtained in this lecture. Okay, so this is the I think now this is the end of our lecture, and I hope that you see or watch the next video, because it is going to be an example of what I have explained now. Thank you, and see you next time.